Welcome to this lecture of calculus. In this lecture, we shall study the Lagrange Mean Value Theorem. We will take the proof of the Lagrange Mean Value Theorem and then discuss some examples related to it. And before going into the statement of the Lagrange Mean Value Theorem, we shall first recall what we have in the conclusion of the Rolle's Theorem. The Rolle's Theorem states that let a function f be continuous on a closed interval ab, differentiable in the open interval ab, and satisfies f of a equal to f of b. Then there exists at least one point c belonging to the open interval a comma b such that f dash of c is equal to 0. So this is the Rolle's theorem. Now let's move towards taking the statement of the Lagrange mean value theorem. So now the Lagrange mean value theorem. Lagrange mean value theorem can be viewed as a kind of a modification of Rolle's theorem, and in fact it can also be treated as the generalization of Rolle's theorem to a better one. This theorem states that let a function f be first continuous on a closed interval a comma b, second differentiable in the open interval a comma b, then there exists a point c in the open interval a comma b such that f dash of c is equal to f of b minus f of a divided by b minus a. So this is what we have in the conclusion of the Lagrange mean value theorem. Now let us discuss its proof, and then later on we will take the geometrical interpretation of this theorem, where we can also clearly see how this Lagrange mean value theorem is the modification or the generalization of Rolle's theorem. So here we take the proof of Lagrange mean value theorem. So this is the proof. First we state what we are given here. So given a function f which is continuous on AB, that is the closed interval a comma b, and differentiable in the open interval a comma b. Differentiable in open interval a comma b. We define one new function here. Define a function g of x, which is defined as f of x minus f of b minus f of a divided by b minus a into x. Then we can clearly see that the function g of x is continuous because it is defined as a difference of two continuous functions. We already have this f of x is continuous, and f of b minus f of a divided by b minus a is just a constant, and constant times x is always a continuous function. And difference of two continuous functions is continuous, and difference of two differentiable functions is also differentiable. So therefore we clearly have g of x is continuous on the closed interval a comma b, and differentiable in the open interval a comma b. So therefore both the conditions of Lagrange's mean value theorem are also satisfied for the function g of x. Now let's evaluate what we have the values for g of a and g of b. For that thing we will see what is g of a minus g of b. So now g of a minus g of b, this is equal to, now g of a, that's equal to f of a minus f of b minus f of a divided by b minus a into a, then minus g of b, and g of b can be written as, this is equal to f of b minus f of b minus f of a divided by b minus a into b. So these are the values of g of a minus g of b. Now we can further simplify it. This is now equal to, now b minus a into f of a, this gives b f of a minus a f of a. Then f of b minus f of a into a, this gives minus a f of b plus a f of a whole divided by b minus a. Then minus, now again b minus a into f of b, this gives b f of b minus a f of b. Then here we have minus b f of b minus f of a into b. This gives minus b f of b, then plus b f of a whole divided by b minus a. Now we can further write this is equal to, now let's compare the terms. We have b f of a here, and here we have positive b f of a. So here we have positive b f of a, and this is negative b f of a because we have minus sign here. Similarly, we have negative a f of a, and here we should have positive a f of a. So here we have negative and positive a f of a. Now negative a f of b, and this is positive a f of b. These two are also cancelled, and finally we have negative b f of b. So this is negative b f of b, and this positive b f of b. So all the terms vanish in the numerator, so therefore this whole thing is equal to 0. So this means g of a is equal to g of b. So therefore the function g of x actually satisfies all the three conditions of Rolle's theorem. So therefore g of x satisfies all the three conditions of Rolle's theorem. Therefore, thus there exists a point C belonging to the open interval a comma b such that g dash of c is equal to 0. Now let's see what is g dash of x first of all. And now we have g of x is equal to f of x minus f of b minus f of a divided by b minus a into x. So g dash of x, this is equal to f dash of x minus f of b minus f of a divided by b minus a. So this is the derivative of g dash of x. Hence g dash of c equal to 0 gives, because we have obtained it on the previous page, g dash of c is equal to 0. So therefore this equation gives us this f dash of c minus f of b minus f of a divided by b minus a is equal to 0. And this obtained by substituting x equal to c in this equation here. So this gives, hence f dash of c is equal to f of b minus f of a divided by b minus a. So therefore, hence here we complete the proof of Lagrange's mean value theorem. Now before taking the examples for more clarification of Lagrange's mean value theorem, we shall first discuss its geometric interpretation. Okay, for the geometrical interpretation of the Lagrange's mean value theorem, we consider the figure that we are given here on the screen. We consider the graph f of x, whose curve is given in this blue color. Then we consider this tangent to the curve at the point, suppose let's call this as C1 and let's call this as C2. And so we have two tangents to the curve at C1, and we have another tangent to the curve f of x at the point C2. Now if we look at this red line here, this red line is a secant that is joining the points a f of a and b f of b. Let's call these 2 points as suppose P, and suppose this is the point Q. So we have a secant or a straight line joining the 2 points or passing through the 2 points P and Q. Now this bold red line is the line segment joining the points A, P and Q. That is the points A f of A and B f of B. So we can call this bold red line is the secant joining the 2 points P and Q. Now if we look into this graph, we can easily see that the tangent to the curve at C1 is parallel to the secant joining these points P and Q, and the tangent to the curve at the point C2 at this point. This is also parallel to the secant joining these 2 points P and Q. Now let's analyze algebraically what are the slopes of these tangents at C1 and C2, and what is the slope of the secant joining this point P and Q. So we mentioned it here. So this is geometrical interpretation of Lagrange's mean value theorem. The slope of the secant PQ is given by f of b minus f of a divided by b minus a, and the slope of the tangents at, suppose let's call this point as a here, and let's call this point as b here, at a and b are f dash of c1 and f dash of c2. Therefore, the Lagrange's mean value theorem concludes that, thus Lagrange's mean value theorem concludes that there exists a tangent to a curve at some point a less than c less than b, where the tangent to the curve is which is parallel to the secant joining the endpoints of the curve. So with this we conclude the geometrical interpretation of the Lagrange's mean value theorem. Now we shall discuss one example. Discuss the mean value theorem for f of x is equal to square root of x on the interval 1, 4. Okay, in the solution, so we are given f of x is equal to square root of x. The function is continuous. Clearly f of x is continuous on 1, 4 and differentiable on the open interval 1, 4. In fact, here we should note that the square root function is continuous for all the positive real numbers. So in particular it is continuous on the interval 1, 4 because it only contains the positive real numbers, and it is also differentiable for all the real numbers where 0 is excluded. So therefore this is also differentiable on the open interval 1, 4. Therefore by Lagrange's mean value theorem, by Lagrange's mean value theorem, there must exist a point, there exists C belonging to the open interval 1, 4 such that this f dash of C, this is equal to f of b minus f of a divided by b minus a. Now here we have this f of b is equal to f of 4, so therefore this is equal to here f of 4 minus f of 1 divided by 4 minus 1. Now let's evaluate what is f of 4. F of 4 is equal to square root of 4 minus f of 1, that is equal to square root of 1 divided by 4 minus 1, that is equal to 3. So therefore this is equal to 2 minus 1, that is 1 divided by 3. Now finally we have this f dash of c, so this implies f dash of c, this must be equal to 1 divided by twice square root of c, because f dash of x is equal to 1 divided by 2 root of x. So therefore this is equal to 1 divided by 3. So therefore this gives square root of c. This is equal to 3 divided by 2. So therefore this implies c is equal to 9 divided by 4. And we can see this 9 divided by 4, this is equal to 2.25, which obviously belongs to the open interval 1, 4. So therefore we have found a point 2.25 which belongs to the open interval 1, 4, and this is the point where the tangent will be parallel to the secant joining the endpoints of the curve square root of x. With this we conclude this present lecture. Thank you.